MergeSort is an example for divide and conquer technique. Here, given an array, you have to divide into equal halves. First half of the array is copied onto B and second half onto C. Sort array B and C recursively. Next, merge sorted arrays B and C into array A. This is a pseudocode for dividing the problem into equal halves. When n is greater than 1, then only you have to apply this merge sort. When n equal to 1, there is no need to call the merge sort algorithm because that itself is in sorted order. Now here, when n is greater than 1, copy first half of the array A onto B. So n by 2, 0 to n by 2 minus 1 elements is to be copied onto B, and next half of the array, that is n by 2 to n minus 1 elements is to be copied onto C. Then apply this merge sort separately for subarray B and then for subarray C. These two arrays is to be merged to get sorted array A. Now we'll see how this merge algorithm will work. Now B and C is to be merged to get sorted array A. B with P elements and C with Q elements. Then A will contain P plus Q elements. So the indices for B, C and A as follows: 0 to P minus 1, 0 to Q minus 1, and for A it is 0 to P plus Q minus 1. Now, when you are merging these two subarrays, either array element B is to be copied if it is small, or if C is small, then array element C is to be copied. For that, you need to know the indices, where exactly or which element of the array is copied onto A. For that, use the indices I, J, K. I for B, J for C and K for A. So all these initially equal to 0. Then compare the element of ith element of B with jth element of C. If this element of B is smaller, then copy that element of B onto A, increment I value. Otherwise, copy the element of C onto A and increment the J value. In neither of these two cases, increment the K value. Now, so this is to be done till all the elements of the B is copied onto A or all the elements of the C is copied onto A. So now, perform this while loop while I less than P and J less than Q. If I value is equal to P, that means you have already copied all the elements of B onto A, only elements of C is remaining. Copy that elements onto A. That is, copy C, J to Q minus 1 to this array A. Similarly, if you are coming out of the loop with the condition J equal to Q, then all the elements of C is already copied onto A. What is remaining is elements of P. You copy from I to P minus 1 all the elements onto A. This is merge algorithm. This I will show with example. This is called recursive tree call. This is done for 8 elements. Then this is divided into smaller subarray with 4 elements each. Then again further divided into 4 subproblems. Again these 4 subproblems is divided into 8 smaller subproblem. Now divide step is over. Now the next step is conquering step. That is, you have to merge smaller subarray to get the sorted list. For this, compare 3 and 8 here. So 3 is smaller, copy 3 first, then 8. Like this, you will get smaller subarrays. Now, I'll explain how these two subarrays is merged. That merge algorithm is explained. I'll explain this merge algorithm for these two subarrays. Now here, B with elements 2, 3, 8, 9 and C with elements 1, 4, 5, 7. So I to 0, J to 0 and K to 0. So now compare the first element of C with B. This is smaller, copied onto A. Again, J gets incremented here. Now it's pointing to 4 now. 4 and 2 is compared, 2 is smaller, so 2 is copied. Now I gets incremented here. 3 and 4 is compared now. 3 is copied now. Now I is pointing to 8. 8 and 4. 4 is smaller, copied here. And 8 and 5. 5 is copied. Next J gets incremented. 7 is smaller, it's copied here. Now K will be pointing to this location. What remains is these two elements. That means here all the elements of C is copied onto A. The remaining elements of B is copied onto A from I to 4. That is I to P minus 1. So from K to P plus Q minus 1. So this is how the merge algorithm will work. Now we'll see the analysis part of MergeSort. In MergeSort, actually you are dividing the problem size into equal halves. So to know how many comparisons is being made in order to sort n elements, you need to know how many comparisons is being made in array of size n by 2. Like that you have two subproblem. Plus, in order to merge that smaller subproblem into sorted array, you are calling the function merge. In that merge, you need to count how many comparisons is being made. So for that, this example I have taken. This is an example for worst case. These 8 elements is to be merged. If you want to merge these two sublists, you are required to perform 7 comparisons. So in the worst case, n minus 1 comparisons is being made. So C merge of n is equal to n minus 1 when n is greater than 1. When n equal to 1, the MergeSort function will not be called at all. So number of comparisons is equal to 0. Now solve this reconciliation. With that, you will get the solution n log n to base 2 minus n minus 1. This belongs to theta of n log n to base 2. Now we have solved this reconciliation by applying backward substitution. The same problem can be solved, or you can say to which efficiency class the algorithm belongs to by applying Master's theorem. So here A value is equal to 2 and B equal to 2, and Fn is equal to n minus 1. This is equal to n power d. So d is equal to 1 here, approximately equal to 1. So this master theorem already I explained many times. So second condition of the master theorem holds here because A equal to B power d. Now number of comparisons required in MergeSort is equal to theta of n power d log n to base 2. Look at here. This is what the complexity in when second condition of the master theorem holds. In this or any reconciliation can be solved by using master theorem or otherwise by solving the reconciliation by backward substitution. Both the method you can solve the reconciliation in divide and conquer technique. So it's left to you how you are solving, either by backward substitution or by applying master theorem. In case if you apply master theorem, you need to write the master theorem first and then find out what are A, B and D values correctly and which condition of the master theorem holds. After that, you can conclude the complexity of the algorithm belongs to which efficiency class. In this example, since second condition of the master theorem, that is A equal to B power D holds, you can directly conclude efficiency of this algorithm belong to theta of n log n to base 2.